So again, welcome. Today we have an exciting talk prepared by Thomas Bednar from Vienna University of Technology, who's an expert in building physics and construction. Thomas has in the past, has I think spent his professional career has spent a lot of his time in Vienna of his professional career, but has had interim visits as visiting researcher and professor in Scotland, Sweden, Italy, Sweden again, and a few times Sweden. You seem to like it up there. Plus, he is an expert in and responsible and contributor to many national and international committees. He's advisor to many international movements and also an expert on the domain. Yeah, without too much further notes and talks, I would hand over the floor to you, Thomas. And I hope, well, I'm certain that you will give us an exciting talk.
Yeah, thank you very much for the nice introduction. I will now share my screen. So now you should see already my first slide.
I think we're seeing the presenter view.
Oh, okay. Mm-hmm. Okay, it erects quite slowly, but I think it should work now. Now you can see the.
Yes, now we have a good view.
Yeah, a warm welcome from my side, and I'm happy to be invited for these EDT talks, which should help the community to get to know each other. As Stefan said, I'm working quite a long time already on, now we would call it digital twins, and but I would like first to give you a short introduction. Where does this all come from? I'm a full professor for building physics, so my basic research area was actually moisture safety in constructions. Moisture safety, you would think it's just to calculate relative humidities and temperatures, but if you think about your own life, it has a lot to do with occupant behavior. It has a lot to do with outdoor climate, especially the future climate. So it's already a quite interdisciplinary problem if you want to assess if you renovate buildings, how the durability will really be. A second very important part for us is building acoustics. Because building acoustics, as you can see here, for example, is in the past, has a lot of measurements have to be done, and it's not so easy to predict the behavior of new constructions, especially if they are, for example, bio-based. You can see here wooden constructions or straw in the construction, so quite complicated. And in both cases, you use a lot of simulation tools. So this is still two important groups in our research unit are dealing with moisture safety and building acoustics. And one of our new topics is, of course, going towards a circular environment, circular building materials. And now you have the whole life cycle of buildings. And a building is nothing, it's embedded in an infrastructure. So if you want to know what is a good future construction, how could you renovate them, you have to also deal with the energy systems. So I will also give you some insights why we ended up with a virtual airport. And in between, we had the chance to see how virtual buildings can help, or to for example, to decrease the energy consumption, enhance the comfort in a building towards one of these nearly zero or plus energy buildings. So when I was looking through the history of the EDT talks, I really liked the talk of our colleague Bednar. He showed the patterns, so I think you will recognize some of the patterns where how we use digital models, shadows, generators, and I'm not sure if I'm showing a digital proxy, but I really liked especially the retirement stage, because is one of our parts in helping to renovate buildings in a very durable way, is also to work together with the authorities for cultural heritage protection. So also our ideas are also driven by keeping our culture when we change our systems. Now, a very old building, and this is a photo, so a very simple digital representation of one of the buildings of TU Wien. And this is the photo has been made before 2012. So this is the old state of a building. It has been built 1970. And that was our chance to show, if it's renovated, how can you really come up with a plus energy building? And if you look for a time scale in such a process, the idea might be already started before 2010. Then you have a design phase, a construction phase. You start to operate the building, and you could, of course, also optimize the operation phase. And but that's only a very short part of the life cycle of a building. So if you look in a broader picture, comparing it with, I was born 1971, and approximately my average lifetime will end somewhere here. My children are a little bit shifted. So this is a very short part, but already visible if such a building is changed. And if we talk about the life cycle, the next change will be here. So would be interesting, how can we get all the knowledge from the design phase after my end of my average lifetime? So then we will need a proxy. And the interesting thing is, or the challenge that we are currently facing, and a lot of talks already talked also about issues on that. If we look to the Austrian greenhouse gas emissions from 1990 till 2020, we did something and learned a lot, but during the next 10, 20, 30 years, our greenhouse gas emissions should go towards zero. So one big aspect is to transform the whole energy system, and part of that are buildings. And so for our university and also for many research groups, it was a good opportunity to see in 2012, how good are we already in forecasting and doing life cycle cost assessments, and how can we use all the digital tools at that time. For this building, which I will briefly introduce then, it has been used by the Faculty of Technical Chemistry, and after the renovation, it was more office buildings for the Faculty of Mechanical and Industrial Engineering. So it's good to have a model of the building because the usage changes. So you cannot really use the old measured data, for example. And that was, of course, an important change in the building. We got some funding, some project partners. Just to briefly mention, the owner of the building is not the TU Wien. It's a special company, which is state-owned actually. And so we are renting the building as a university. So also this is an interesting problem. So you have two stakeholders, different views on the possible solutions. One is more interested in the life cycle costs. One is more interested just in the building investment. So might be good that they have a good way of how to find a good solution. Now, if you want to decrease energy consumption, everybody now knows PV could be a possible idea, a possible component in the new system. So we checked how much energy could be produced at the roof and also at the facade of the building. And here you can see one first very simple digital representation of the surrounding buildings, and a model that is accurate enough to estimate, for example, the electricity production. So we ended up with that we will have around 250 megawatt hours per year on roof and facade. So that was the forecast, which has been done 2010. The solar gains or solar energy estimations will not really change a lot, but from year to year you will have some deviations. but that was actually the first important assessment, because now you know how much electricity you really have on site. And that, if you take a look at the end, it really came up that it's a good idea to have a roof and a facade integrated photovoltaic system. And in that year, it was actually the largest building integrated photovoltaic plant in Austria. And if you visit Vienna, please join one of excursion, or you can even visit the building on your own. So, for example, you can see in the staircases how nicely it integrates into the facade. And it's not so easy to see the roof, but might be interesting to take a look at the building. Now, the challenge is that you only have, if you convert it to non-renewable primary energy, kilowatt hours per square meters gross floor area, now you have a target of 61. The old building had much higher consumption, but as I told you, the usage changed. So now you could estimate a typical office building. A typical office building would use around 458 kilowatt hours per square meter. So no chance actually to really cover it over the year. And now you have to go through every component in the building. And this is actually now, what should a digital twin of a building contain? Okay, let's start with the facade. Why do I start with the facade and not with the load-bearing construction? Because in our building, the load-bearing structure was the one from 1970. So we just had the chance to think about the facade, totally new one. And of course, you have a lot of different aspects. If you think about the facade, you have to, for example, minimize heat losses in winter to decrease heating energy consumption. You could minimize solar heat gains for the summer performance, but you should always think about maximizing daylight. So this is, you now have 3 tools, for example, to assess the performance. And then you end up with a lot of geometry. And some parts of the geometry are have a focus from the structural engineer. Some part is in the focus of the building physics engineer, and some is in the part of the architectural design team. So already in minimum 3 different teams or project partners have different focuses on one small part of the building. And of course, then you end up with a lot of different materials, costs, performance, and so on. Now, as this is not a normal facade, but it should also generate electricity, there's another group that deals with the performance of the PV modules. So the higher the temperature of a PV module is, the lower the electricity output will be. So you could think about ventilating those PV modules, but if you increase the thickness of the ventilation area, you increase the costs because of the structural engineering part. So this is the next optimization that you have to think about. Then if you have now a very airtight, very good insulated envelope, but you want to increase the heat losses in summer, a good idea is to use nighttime ventilation, and there are now you have 10 different options to do this, and you have to assess costs and performance. And we ended up with a ventilation that is using 10 windows, so 1 window per floor, and 2 shafts, which have already been there, also in the building from 1970. And so if it's good idea, so if indoor temperatures are already a little bit higher than you would like them to be, and the outdoor temperatures are lower, so could be also in April, May, then during nighttime, normally, windows open and the shafts open, and without electricity use, you can get rid of some kind of the excess heat. So it's a quite interesting performance calculation. So how often can it be used? So you have to use the whole building topology, all the airflow aspects of the different components to get an idea on the impact of the operative temperatures now during the year. As you want to maximize the daylight entrance into the building, here you can see now a photo from one of the floors, and you can see that the walls between the internal part of the building and the offices are made out of glass. Can you imagine this? This is actually quite cost intensive, but it has two good aspects. You can have more daylight into the building, so you can reduce the electricity for lighting in the internal part, and you can also couple them thermally. But now the question is, can you avoid cooling devices in the offices already? So now you need a hydrothermal building simulation where you can combine all these aspects. And this has to be done in a model which is room-wise, because you really need the different thermal transport mechanisms and to really see for each room in different scenarios how the temperatures will evolve, and do you need heating or cooling, and can you avoid, for example, special cooling devices. And at the same time, of course, you also have to think about what are the colleagues are going to do in these rooms. So how many printers, how many tea kitchens, how many workplaces, what kind of equipment are they going to use? So it's a good idea to have a room-wise model of the whole building, and a lot of variations you already might recognize that all the design team members can have good ideas, and so you can, the amount of variations are growing that you can check for costs and benefits. Also, one important aspect of such a building is the ventilation system. As Vienna is a city, cities are normally not so silent, so it's a good idea to have a good indoor quality without opening windows. And especially if it's very cold outside, you could use heat recovery to decrease heating energy demand. And also during very hot periods in summer, it's a good idea to have also heat recovery. So here you can see, first of all, this is a picture of the two rotary heat and moisture exchangers. Because we came up with that it's a good idea to have two exchangers, one just exchanging heat and the other heat and moisture. And here you can see a picture from the outside of a central air handling unit, where you can see a lot of sensors and also actuators, because now it's the question, which of these wheels is in operation during which part of the year. And now, going through all these aspects of a building, you start with 458 kilowatt hours per square meter. And now if you help the design team to optimize and to find different ideas, new technologies, and estimate costs and performance, and if you help them to optimize 9,300 components, then there's a technological potential to decrease the energy amount for heating, cooling, warm, hot water, ventilation, lighting, the elevator, different components for building automation, also the file servers and the power supply and the telephones and the switches on the internet connections, the workplaces, copy machines, and also the coffee machines at the end. And so it's quite interesting, because normally, and there are also patterns in designing. Normally, buildings are designed by design teams as they designed the last one. And now you might have an idea that if you put a digital representation of the building in the middle of the team, and to help them to find good solutions out of the box, then it might be very interesting. Why do we call it a plus office building? Because in a university environment, we use a lot of simulation servers, and they also need a lot of energy. And that's a special aspect to use green IT. But in our building, At the end, we moved all the simulation servers out of the office rooms into a server room, and we are actually heating the building out of the server room. Now, if you combine usage and building, then it's easier to recognize why we call it plus plus, because a plus energy building covers its own energy need for heating, cooling, ventilation, and if it's plus plus, it could also cover the usage. So that's a real challenge, because you can see the technological potential is for Vienna in the year 2012. It's a very low difference, and that's the technological potential. So if you then call out for contracts, then you might end up with a little bit different components. So on top of that, during this process of finding a good solution, then of course you have at the end a company that constructs the building, and you have a process during the building construction phase to handle aspects that pop up. It does not work, what's happening, and who is responsible, who has to take care on that. And so we actually installed a special process to handle these upcoming topics, because we had to keep and track in our digital model what's the difference between the original design decision and the real construction phase. And this is on a time schedule. It's not so easy. And normally people tell you it takes 2 years until a building is really in a good state. And here you can see more details, because we recorded all these topics that popped up. You see here in 2014, our colleagues moved into the building, and then 1 year and half another year. And then actually a lot of aspects were recognized and could be solved, because the problem is the software of the building automation is actually produced the first time, so they cannot really test it. It's tested by the real behavior of the building, and people that complain, for example, oh, my room is too cold or my room is too warm, and then you can start to investigate what's happening. The good thing is sometimes people are happy if they are not part of the problem. So it was good for us that we always had the simulation model of the building to really think about, okay, what should be the correct state, of what kind of temperature should there be in the rooms. So we could really help to identify who has to do something. So who has to check the valves, or is it really the sensor in the room, or is it just the usage of the room? And one part of the strategy was, as we during the design phase, it was clear, if we want to have a very low energy consumption, we should go for energy efficient equipment. And here the green graphs show you the temperature during a quite hot period in a group room where they use very energy efficient equipment. The dots are the daily average, and the dashed line is just the maximum temperatures. The design limit actually is this red limit here at 26 degrees Celsius. And you can see that a group room with typical office equipment and some of the workstations still in the room it's just 2 to 3 degrees warmer, but for people that's very recognizable. So they would actually complain, oh, it's so hot, there must be something wrong with the building. And the good thing is that in some of the floors, people moved in already with energy efficient equipment. So if you show them, okay, let's look into another group room, that's colder. So then they experience that they really have to take their old equipment and change it to the server room, and in the server room it should be changed to energy efficient equipment if it's already at the end of the life cycle. And in that way, it's easy to identify if something pops up which is the correct measure that has to be taken. Also, one important aspect is to have a digital twin for a photovoltaic system, because all the inverters, they are not so stable. Sometimes they stop working. So the electricity which is coming out of the system into the grid is reduced, and you can easily find out if you have to check them if you compare the measured and also the with the simulated monthly, for example, electricity production. So that's also the companies that produce PV systems are already having quite good monitoring systems. So it's very highly recommended to, at the same time, to have because it's not so complicated, to also to calculate the electricity production, and to really to check that your system is in a good shape. And if you then take a look at the energy consumption in the floors, you can see here from 2015, 16, 17, 18, that it decreased, and we were very happy that we already had one floor where one of the institutes moved in with very efficient equipment. So that's also some kind of reference floor. And you can see that all the others changed. We could not motivate them to change all the equipment, but at the end, we are very happy, because this is the dashed line here is actually the electricity produced per floor. So if your consumption in one of the floors is only half of that, you are very happy, because the rest has to be used by the other building services, for example, heating, cooling, and lighting. So in that, so we used already quite detailed models from the first minute of the design phase, introduced them into the design team, and also to keep an eye on the production of electricity and to check temperatures. So during the process, it was not an automatic digital twin which compares monitored and measured results and does something, but it was all people in the middle to use these the measured and also the simulated results. If you measure something, we learned, and all other colleagues learned around the globe, that if you measure something, even please check also the energy meters and how they are putting data into a database, because you can easily install the wrong parameters in the meter. You can easily mix cables, and you can easily change the names in the database, that at the end you don't really get what you really wanted. So that's also good to have a digital representation of the building and to compare it, and also some other checks to see if the whole system of measuring a building is really in a good state. If you are interested in details, we have a publication in the Bauphysikkalender. Unfortunately, it's in German, but the new artificial intelligences for translating might help you. Otherwise, please come back with some questions. We ended up with a lot of data in databases and some digital twins, and concluded, as we were very close to the technological potential you can see here, we concluded from a technical point of view, okay, there are some open tasks, for example, details in hydraulic systems, details in the ventilation systems, the intuitiveness of the control devices for the occupants. Okay, some old stuff should be changed, because, for example, here, I'm not sure if you would guess it in first place, that the telephone system in an office building shows up in the electricity demand in quite a big part here. Yeah. But that's from a technical point of view. From the way how it is designed, how it is constructed, and how is it operated, it was clear that all of the team members, 15 to 20, they have to use a lot of information from materials, constructions, building service system, many of them have to use the same or similar geometry of the buildings and occupancy, it's different scenarios for occupancy. And they have to use a lot of methods to assess how close are they to requirements. And one of the requirements are life cycle costs. If you look from the point of the one who has to rent it and to operate the building, or from investment, just then it's part of these life cycle costs. But they all use a lot of methods, from structural safety, thermal, visual, acoustic comfort, indoor air quality, has a lot to do with occupant behavior. Then, of course, we have to predict energy use for heating, cooling, humidification, dehumidification, fire safety, how fast is the building evacuated, how will be the performance of different buildings, and also the usability. So, for example, cleaning, how easy can it be cleaned, because that goes into the life cycle costs and so on. This needs a lot of geometry. So currently, they all use their own tools, and then they are confronted with quite complicated problems. So part load behavior, because that's then we could also solve these issues in the hydraulic and the ventilation systems. Okay, green IT, how is this really operated and installed and so on? And building automation. So beside the geometry and all the technical parameters, you also, from the first minute on, you have to think about building automation in two kinds. How intuitive is the control for the occupants and for the operators of the building? And also, how good is the design idea transported into the construction phase and the operation phase at the end? Think about the night ventilation system. I told you it's, just open the windows if it's cold outside, but when do you close it, and what happens during fire safety, and what is the real, how should I really operate my building? Because it depends on the weather in the next few days, if it's a good idea to cool it more or less. So it's, at the end, it's not so easy to have a very efficient operation. And if the designers thought a lot about it, it would be good not to lose this knowledge. So we concluded it would be nice if they all would have a common environment where they can get an idea on all their aspects. So at the same time, we also had a doctoral school on what is the future of cities. And we came up with the idea, let's start to develop a teamwork environment. And especially at the end, we would formulate a metadata model for a team to handle the future of buildings, cities, infrastructure, and to analyze it in scenarios by using all these different simulation tools. And I will then also quickly show the virtual airport Vienna, because when all these projects started, luckily we got a call from the Viennese airport and they took over the idea. And now let's take a quick look. If you want to know more about URBEM, which is the doctoral school on the urban energy and mobility systems, where these 10 PhD students worked on a model of a city. As an example has been Vienna. You can find a lot about this at the website URBEM, www.tuwien.at/urbem. And after that, we were even more convinced that we really need a big open BIM, which can handle realistic parameters and realistic system behavior. So not only building information modeling for simplified tools or simplified methods, but for the future methods, which can handle much more realistic the behavior of different systems. And we called it simultan because on one hand, people have to work together simultaneously. On the other hand, they have to use a lot of simulation tools. So we found it a nice idea. Let's call it simultan. And as you know, if you once put down a name, then it will last forever. So it's still called simultan, and we can always think about what's really in it. And the first after a few rounds talking to all the stakeholders, the team was quite convinced that the basic idea of such a metadata model will have some generic components. The components can be organized in networks, and you have to couple geometries to it, but in a very generic way, because we should be able to put here the building, the topology of the building, the basic constructions, the building services. And so at the end, we were quite happy, and there were some publications about this. And we ended with a proof of concept and were asked by the airport of Vienna, oh, you are having a building that does not use electricity anymore. We want to build buildings, but we don't have electricity. So please help us to copy your idea. And we said, no, we should not copy the idea of the building, but we should copy the idea how we came up to the solution. And now let's take a look. Where's our airport? You see Europe, Austria, Vienna, and a little bit between Vienna and Bratislava, there's Flughafen Wien. And that's the digital representation you find in Google. Perhaps this is already a quite old build, but picture then if you now would take a look in Google to the airport, it might look different. But the airport itself has a very good digital representation because, and you might guess why they have to make a very good, very detailed photogrammetric measurement of them, because they have to document these all these different paintings on the runways to tell the authorities that the runway and the signs and is very correct. And at the same time, you can get this, because this is a photogrammetric and laser scanned airport, so it's many points. It's not so easy to really render them. On my laptop here, you can see you saw a small PV plant, which is already in operation, and you can see all these buildings. Okay, quite nice. And now even the advertisement switches, because it takes a little bit of time until you have all this data. And so you can, this is some kind of snapshot of the airport, looking at the geometry you can measure from outside. And that's nice, but that does not really help a design team to have some forecasts, but it's a lot of information you could use. All the airport staff, they have a lot of ideas. And when we started to cooperate with them, they had, you can see here, different new buildings in different phases where they thought might be interesting to have them. And for example, especially here you can see 4 buildings. That's an office building and two additional, or one renovated terminal, or 2 renovated terminals and 1 additional building here. And the interesting thing is that the office building, so the renovation of the first terminal, the second terminal, and the new building would already bring their electricity consumption into the red zone. So no chance to have a stable electricity system. And that was the initial estimation of the typical design teams. And at the same time, they knew that last time they designed the building, it just used half of it, as it has been in the forecasts. And then we could help them to understand what's the real situation and why do designers come up with these estimations. And that was the possibility for us to come up with a digital representation of the Viennese airport, to make building simulations, to make grid simulations, and to show them for example, the load on the different cables and different parts of the heating and cooling district system. And also we could include these new buildings. And you can see if you make forecasts, you can see, okay, it's still less than 100%. But if you go more into the future and more buildings come up, then you can see, okay, you are reaching here close to 100%. So there will be a limit. But on the other hand, by starting to analyze the existing buildings with them and to split the electricity demand and due to the simulation to help to understand which aspect of which of these buildings has which impact on the overall performance, then we could also help the design team to find different solutions. So we could reduce some electricity consumption in the existing buildings. We could reduce by using another set of technological optimal solutions for the terminals and also for the office parks. And so at the end, they could avoid starting to install or to stopping their development or to to start new power plants actually at the airport. And they also they could in meantime realize, for example, the Office Park 4, and you can see it's quite a innovative construction. And at the end, we also had the next level of our environment based on the metadata model simultan. Here you can see the geographical representation of the airport. If you double click on this building, you come to the more architectural or more civil engineering description of the building, and you could click then down to each component. And after that, they also installed a big PV plant, and now they are happy to be looking on their balance. They are already for their operation, they are CO2 neutral. But still, of course, they have to do a lot, because if they want to build more buildings, then they have to reduce the costs. And in that way, it's a good idea to have a digital representation and always to compare the measured and the simulated results. So we were quite happy with our data model. It has been enhanced more and more. And so helping by strategic planning and helping in the efficient operation of buildings, it's quite easy. And we found that there's still a gap in the design and construction phase, especially because you have to go into more details of the geometry of the construction. And that's our current approach. So we have in this green box, it symbolizes the metadata model, where you can replicate actually the data models of different tools. Tools might be calculating operative temperature, heating loads, loads on infrastructure, and so on, doing assessment of how fast can you evacuate the building, and so on. And you can, of course, exchange data to databases and in different formats, but in this open data model, you can store all the components and nothing has to be stored twice. And one of the developments is now to enhance the geometry. I will talk a little bit about this in the next few minutes. And for these, how to use this metadata model, it's already an open source project in GitHub. So I'm happy if you get in contact with us, because we are currently using it to think how has this to be enhanced, for example, for subsurface engineering, so very large structures. That's one of the projects together with the Montanuniversität and also JKU Linz, which is now in the final phase, where we are going to now to build a small digital twin of part of a subsurface structure. And this will be a real digital twin because it's in the laboratory scale, but it will include measurements and control systems. And you can see how you can set up the digital twin at the same time you set up the measuring devices and so on. Our focus here is, for example, to couple it to look for airflow, fire, smoke propagation forecasts, and so on. And we could also show together with an engineering company that this metadata model can, for example, hold all the necessary data for a widely used hydrothermal building simulation tool, EDT. Some of you might know it, and also a tool for structural engineering. We use, for example, RFM. And so from one digital representation, you can get the data for EDT. And if you take a deep look into the picture, EDT needs, for example, internal volumes and not the external ones. And the structural engineering tool needs some abstract geometry. So even those two widely used tools have two different geometrical representation of the geometry of the building. And both will deliver a lot of results, and the interesting results, you should be able to get them back into your metadata model, because if somebody in the chain in the future has to know it, then it should be kept there. So you can read about this development in the publication from last year. And now, as I also talked about building automation, which is the software in the software for us, we also have a project together with Sauter, where we were together with our colleagues from informatics, building automation group. We were thinking about what is necessary in a metadata model. If we already have the geometry, we have all the information, how it is used, the components, building technology, and how can we add the control and automation aspects into that model, that at the end, for example, in the design phase, we can use not only the constructions of building services and so on for the simulation, but also that we can keep the most important information on the ideas on how the building is operated actually for the simulation, and at the end, in the construction phase, also for the implementation into the real automation system. Of course, it would also be nice to have ideas back into the model. So for example, if some contractors have a good idea, then they could show how it compares to the original design solution. But that would be actually then one of the next steps. So this is, I think, one of the steps that it's quite nice that it's now first ideas can be formulated and can be shown how you can do it. And one of them, the last points I would like to talk in the last few minutes is now the question on how to enhance trust into digital representations. Because currently, the problem is if you get an export in a data format from another partner in your design project or wherever, the question is, how can you trust those data? And I think there are some already ongoing activities that could really help. And we had one publication, and I'm happy that Galina is also part in that meeting here. So if you want to talk more about this, she might help me, because I'm now completely out of my field. And just to give you a short view from my side on that topic, it's a typical problem that different experts might use different guidelines to do something. And for example, in a tunnel in the operational phase, air quality has to be assessed. So there are two different guidelines, how to measure tunnel air quality and how to measure carbon monoxide, special method. So on a more abstract level, there is you have a team, partner 1, partner 2. They use two different guidelines. They use two different tools, and in the background, they will have a data model. Sometimes it might very often happen that part of the data models overlap, and one will be the one who is the original author and the other one has to trust, for example, this part here. Now, if you move into a next phase, then there might be other partners. They might use the same guidelines, but different tools, or use additional guidelines, additional tools, and the problem gets even more complicated. Normally, or what is very typical, they start to look into a PDF report from another one, because that's written. And you can, in the future, you can reference on this written report. The partner A or partner X2 told me that something is. And so they setting up their own models, and they don't trust really the digital representation of the others. And the second question is, now if you have the data model for the tool A1 and you have, and this is actually able to calculate the same thing that the data model of the tool A2, how can you really trust, how can you transfer data in a trustful way? And now if you think about how it is currently done, currently there are standardization bodies or other bodies that produce guidelines. Normally it's a PDF. In the future it was hard copy paper, but now it's a PDF. If it's a good guideline, you have a lot of validation exercises. If you have a very good guideline, there are very many validation exercises, because each aspect in the guideline should be covered by a validation exercise. And for example, the Austrian Energy Certificate reference tool contains about 1,000 reference cases, and this is just the default part of the calculation. So currently nobody had time for the full version of validation exercises, even in the non-default parts of the calculation. But currently they are at the end a PDF, and then somebody is software engineering tool A1 or 2, and they produce a PDF that they can reproduce the validation exercises in these guidelines. And of course, as usual, they have their own data models in the background. But they actually just calculate guideline A. Now, how could we use these guidelines? And that's in the publication of Galina, Patrick, and Bernard, you can read it. And how could we now use, for example, these guidelines in putting more trust into the data models in the tools? And the idea is to go to a graph representation of, for example, the equations and all these quantities, and then to anchor the parts in the data models to these graph representation of the guideline. You can do this with different guidelines, and more can be read in the publication here. So the idea is not only to have a guideline, but also to have a data model for the guideline, and the anchoring representation, the tree representation of the guideline. So we have a reference data model, which you can already anchor. And then you can also anchor the data models of different tools to that guideline. And in that way, together with all the validation exercises, it might at the end be easier to exchange information in these three data models. But if you start in one standardization body, of course, you could also enhance this, go to the next guideline, enhance the data model here, enhance the anchoring methods, and you can continuously get more trust into digital representations of actually guidelines. So thank you very much. I hope you got some impressions of our last a little bit more than 10 years. Personally, I would conclude it's really was a good idea, which we started 10 years ago, to go for a new way of data modeling. We ended up with a metadata model, and we are quite happy. Also in our teaching, we can already use this metadata model to help students to work together, even if there's not a predefined final tool for everything. So they can start to build up their own simulation tools, set up the data models, compare it, and then start the teamwork. Currently, we are finalizing the multi-geometry, which means that geometries are referencing geometries, and you can work in a team on geometries and also connect them to all the data. Anchoring of guidelines is and validation exercises in the version 4.0 is, I think, a very important step for the next future. And then go away from PDF formulated algorithms. We would motivate open source codes, of course, very well documented, and hopefully we can come up with some examples, because now the energy certification in Europe has to be rewritten. So this is actually a hydrothermal building performance simulation, and then other aspects could also switch the way how they integrate with data models. Yeah, thank you very much, and I hope we still have some minutes for discussions. Thank you.
Indeed, thank you very much. I will stop the recording here.